So about hard disk. So we discussed about hard disk a few weeks ago. So hard disks contains of several disks, which we call as platters. So in platters, how the data is stored is actually the structure we imagine is we assume that there are tracks, and in the tracks there are sectors, as you can see from here. So the yellow color ones are tracks, and the ash color numbered with 1 is a sector. So sector by sector, data is stored in a hard disk. So you can see when you calculate this capacity, this feature is revised. So you can see how many components are in this equation for the calculation of the capacity. So this multiplication sign should go here. So number of bytes per sector into average number of sectors per track. So it depends on the structure we think about. So, so let me explain that using this whiteboard. So I think you can see the whiteboard, isn't it? So we know we have a disk like this. So disks have tracks, and in the tracks we have sectors. Okay. So number of bytes we can store in a sector, it's the first term, and then it's multiplied by the number of tracks. Number of sectors you can include in one track, that's number 2. So you can see we are evolving starting from the smallest unit, smallest place, or smallest space which we are storing data. So it's this sector. Okay, so number of bytes we can store in the sector multiplied by the number of tracks. Number of sectors we can include in one track, and then it's multiplied by number of tracks we can include in one surface. Okay. Then how many surfaces are there for a single platter? So likewise, it's evolving. You can see we are starting from the smallest unit, and then according to the structure we are developing the equation. So and then lastly we add the last term, platters per disk. Okay. So from this computing disk capacity, so to understand further, I asked you to do an exercise. So that is this. Calculate the capacity of the hard disk with the following specifications. For a sector, there are 512 bytes in that particular hard disk. And for a single track, there are 1000 sectors in that hard disk. And for a surface, you can find 80,000 tracks. And for one platter, there are 2 surfaces. And for one disk, there are 5 platters. So what you have to do is actually, to calculate the capacity, you have to multiply one with the other. You can see you have multiplied the all, because you can see these structural relationships. There are some certain bytes you can store for a sector, and then there are certain sectors per track, and there are certain tracks for surface, and there are certain surfaces for platter, and there are certain platters for disk. So likewise, using the relationships, we can calculate the number of bytes it can store, and then convert that into gigabytes. Okay, so there's nothing difficult there. So apart from that, there are several other measures we use to calculate the speed of a disk. So the other main measure we use to calculate the performance of a hard disk is disk access time. So this disk access time depends on the way how the data is accessed. And you can see the behavior of hard disk. Hard disks rotate around a certain axis. So, so disk surface spins at a fixed rotational rate, and this data is read or written using a read-write head, which is attached to the end of the arm, and it would fly over this disk surface like this, radially. Okay, so it's trying to find the sector and the track by moving radially. It would move radially while the disk spins at a fixed rotation rate. So now you can see how many factors do we need to consider when we are calculating the disk access time. So we need to have look at the seek time. Seek time is the time to position the head over the cylinder containing target sector. So first we have to put or position the head on the corresponding track. So that is actually that requires certain time, which is called the seek time. Okay, the average typical seek time is 3 to 5 microseconds for a typical hard disk. And the second measure we need to consider about is rotational delay. In rotational delay, it's the time waiting for the first bit of target sector to pass under the read-write head. So once we have identified the certain track, we need to find the corresponding sector on that track. So for that, we need to rotate, wait until the disk rotates to the particular sector. So that is called rotational latency. And the transfer time is the time to read the bits in the target sector. So on average, it's 0.006 microseconds for 10,000 RPM disk. So now I think you understand that we need to consider three things. We need to first find the corresponding track, and then by moving radially this read-write head, and then we have to wait until it rotates to the particular sector, and then we have to consider the transfer time of the particular number of bytes or bits stored in that particular sector. Okay, so those three factors you have to consider when you are calculating the access time. So these three factors are named as seek time, rotational latency, and transfer time. So those are the main three factors that would affect the average access time of a hard disk. Are there any problems? If there are any problems, please let me know. Okay. So up to now we have discussed about two things: how we are going to compute the disk capacity, that's straightforward, and the disk access time, which depends on three main factors. Okay. So so from now on, we are going to move to CDs. So we have discussed up to now about the hard disk. So about the compact disk or CDs, so data in the CD is normally stored as not similarly as hard disk. Here we use compact disks are called optical disks because we use light or light rays to read and write data in a disk or CD. So these data in CDs are stored as a set of LANs and PIDs. So what's a LAN and what's a PID? Maybe in previous lecture also I may have mentioned this. So if I move to the whiteboard, so if this is a CD, so this is a normal CD which you use to carry your data here and there. So in the CD, if you look at the cross section, the data is stored in LANs and PIDs. Okay. So if you use look at this closely, what is a LAN and what's PID? It's something like this. Okay. So so assume that this is this surface is the surface which you have a label on it. Okay, so there's a label on top side. So if you look at from this side, so these are lands and these are pits. Okay, so these are lands and these are pits. So when the laser beam shines, how do we store zeros and ones is the problem. So when we are storing data, what we store is zeros and ones, isn't it? So how do we write data? So we create lands and pits. Okay. So we need two states because to store 0 and 1, we need two specific states. So for that, we use lands and pits. It's something like this. So we use a laser beam to store data. So when laser beam is shown on the surface, what would happen if it so if the surface is a land, it would reflect. Okay. However, if it incidents on pit, what would happen? It did not reflect. Okay. It would be absorbed inside like this. Okay. So these two states are used to store zeros and ones in a CD. Okay. So that's technique used in CDs to store data. So how do we read? So reading also, when you're writing, you make corresponding lands and bits corresponding to zeros and ones. And when you're writing, you make these lands and bits. This code is something like this. So if you use land for 1 and a bit for 0, so you would make something like this. Okay, so this is, you are looking at from this side. Okay, so this is a land, this is a bits. Okay. So likewise, so you are creating lands or bits correspond to the zeros and ones you use. However, when you are reading, what you do is you shine a laser beam. You use a laser beam, and when the laser beam incidents on a land, it will be reflected, and we can identify that as 1. And if when you shine these laser rays on these pits, what will happen? It will be absorbed, so there will be no any reflection, so it indicates 0. Store. Okay, those are the two ways which we use to store data in a disk. So when reading a CD, laser beam shown on the underside of the CD, and the top side of CD is the label. And when there's a land, it's reflected, but when there's a pit, it is not reflected. Okay, so the reflection and not reflection is used as the two states of 0 and to represent 0 and 1 in a CD. So when the light reflects back, it will generate number 1. And when light fails to reflect back, it will generate number 0. Okay. These reflection related transitions are used to binary 1 and 0. So in your writing, what you do is we use a laser beam to burn these bumps, either zeros or lands. Okay. And standard CDs are of diameter 120 millimeter, and it can hold up to 80 minutes audio. It means 700 MB. So that's a very well-known famous fact. And there are different types of CDs: CD-ROM, CD-R, which are writable, and CD rewritable. CD-R and difference between CD-R and CD read-write is CD-R is write once, but CD read-write is rewritable media. Okay, VCD are the video compact discs. And if you look at the cross section of a CD, it will look like this. So label is on the top, and these are the pits and lands. It would be safely covered with the polycarbonate plastic layer. So not like in a hard disk, in a CD, the data is stored one after the other in a spiral. Okay. not as in hard disk. In a hard disk, we store data in tracks and sectors, okay? So here we store one after the other in a spiral. And these bumps, the diameters of bumps are in this range, normally 0.5 microns width of the bumps, and the difference between two rows or spirals is 1.6 microns, and those are the dimensions of CDs, pits and LANs. And DVDs can store more data than CD. So the long term is digital video disc or digital versatile disc. In video discs, they are developed for movie industry, which should afford a lot of movie video data. And digital versatile disc is, on the other hand, can be used for any purpose, any other purpose. So it has a larger capacity than CD. It can store about 4.7 GB compared with 700 MB of data in a CD. Okay, a lot of. It has the technique how you can store the same size CD, a very large amount of data compared with the CD. So the technique is with these pits and LANs, it uses smaller pits and LAN when compared with the CD. So when the LANs and pits become smaller and smaller, you can store more and more data on there. Okay, so they are much closer and 4 times denser than the CD. And the DVD drivers use short wavelength laser beam, which is 650 nanometers. And there are again types of these DVDs available. It can only be read and not written, and DVD-ROMs and DVD-R can record data only once, and then it would function as DVD-ROM. And then read-write, they can record and erase data multiple times. So that's about DVDs. So apart from these two popular CD types, there's another type which is used recently, not recently actually, it is invented in 2006. So it has stored a very large amount of data. So single layer disk can hold around 27 GB, and a dual layer disk can hold about 50 GB, and triple layer disk can go about 100 GB. Okay, so there are some examples given here for you to think about the size of this capacity of the disk. So we need to use blue laser instead of red laser. For DVD and CDs, we use red laser, but for Blu-ray discs, we use blue laser. The name also is referred because of that. So it would have smaller pits and smaller beam and shorter track pitch. So what is track pitch? Track pitch is this value between, okay, the difference between two spiral tracks. Blu-ray also has a higher data transfer rate of 36 megabytes per second, and DVD has only 10 megabytes per second. And it is also, there are several different formats of it available. Blue disc, ROM, blue disc writable, recordable, blue disc rewritable, and again RE rewritable for HDTV recording. So if you compare these three things, you can see the track pitch is 0.6 microns for these CDs, and DVDs it's 0.74, and for Blu-ray discs is 0.32, which is becoming smaller and smaller. And the pit length of the pit is 0.8 micrometers for CDs, and 0.4 micrometers for DVDs, and for Blu-ray disc is around 0.15 micrometers. And the storage density increases, you can see, as seen here. So the main techniques we use are actually shorter pit lengths and shorter track pits. And because of those features, we have to use this sharp beam spot. So for that we can't use red laser in blue rays, mainly because it can't create such a small beam spot. So for that we use a blue laser rays. Okay. So that's about the CDs. Are there any problems? If you have any problems, please ask me. So these facts are theoretical, and if there's any problem, you can ask me. So I'm not wasting much time on this topic. And when you're talking about the flash memory, so it's actually the most famous type of memory we use these days. It's non-volatile computer memory, not like in the other media like in RAM. Comparably, non-volatile means when there's electricity there or not, you can store data there. So this is a specific type of EEPROM, and this is solid state storage device. So there are no moving parts, noiseless, and it will offer fast read access time. So because of that, we all tend to use that. Okay, smaller in size, so light, handleable, and to store information in an array of memory cells made from transistors. And there are different form factors of this coming. So the most popular SD cards and multimedia cards and compact discs, compact flash are some of the popular types of flash memory. And USB flash drive is among all is very popular, and it is removable and rewritable, and there are reasons why this is popularly used among people. Smaller in size and lighter and faster, and it is more durable and reliable because of the lack of moving parts. Okay, and it would have a printed circuit board, as you can see in this picture, and one indicates the connector. So the printed circuit board would carry the circuit which is required to store data to the chip. This is the chip. Number 4 is the flash memory chip, which will be store data in. And number 2 is the controller device. And this should have an indicator light as you always see when the data is in use. And number 5 is the clock or the crystal oscillator. And read-write protectable switch is optional, and it does not come with most of the devices these days. Tertiary storage, so that's about the USB flash drives. And up to now we have discussed about secondary storage devices. Mainly we discussed about what? Hard disks, then CDs, we discussed about several CD types, and then about the flash drive. So, so tertiary storage device is, when you compare to the secondary storage device, is huge. Okay, the main objective of tertiary storage is providing a very large capacity at a low cost. We need to store a very large amount of data sometimes. So tertiary storage devices are available at that time. Okay, so it's, I mean, the main difference between secondary storage and tertiary storage is that if you look at this picture of a tertiary storage device, which is a large tape library. So there are tapes stored on each rack, and you can see there's a moving arm. Okay, there's a robotic arm moving back and forth. So by moving here and there, it would find the required tape and provide for the particular purpose. Okay. So the main difference between secondary storage and tertiary storage is with this robotic mechanism. It will mount and dismount removable mass storage media. Okay. And data is often copied to secondary storage, and this is used for archival of rarely accessed information. However, it would be slower than secondary storage, and it would be used for very large data stores like tape libraries. It would be accessed without human operators because it has a robotic mechanism to access what data is required. So apart from this, there's another storage type, offline storage, which we have the devices we have discussed so far. So the offline storage is a computer data storage on a medium or device that is not under the control of processing unit. So a flash disk, a flash drive, which we discussed just now, is also a type of offline storage. Okay, the medium is recorded in a secondary or tertiary storage and then physically removed or disconnected. Okay, it must be inserted or connected by a human operator, not like in tertiary storage, and it is not under the control of the processing unit. So those are the main 2 points you need to understand about offline storages. In modern personal computers, most of the secondary devices storage, tertiary storage media are also offline storages. Okay. Examples are, as I told you, flash memory devices and optical discs. Okay, so there are some exercises for you. So may I move to the next topic? So these facts are straightforward. If you look at the internet and some textbooks, you can read these things, and that's why I actually didn't take much time on explaining them. So the next topic is about addressing modes. So about the instruction set architecture actually. So this, the content of this presentation are mainly taken from this reference book, Computer Organization and Architecture. So what's the difference between organization and architecture? So previously also we discussed about this to some extent. I think you may remember that architecture is the interface between hardware and software in simplest words. Organization is related with the components and connectors in the system. Okay. So the architecture is the interface between hardware and software. There are different architectures defined, like for the instruction sets, we have different architectures, and for registers and how to access the memory architecture. So likewise, there are different architectures which would define these interfaces between hardware and software. Okay. And there are many organizations for a single architecture, like as an example, Intel x86, Pentium Pro are some architectures, organizations for architectures. So from these architectures, today's topic is about instruction set architecture. So what does the instruction set architecture mean? It's actually, in other words, the specifications required to program the machine. So what type of addresses are available, and what instruction does the machine understand? Are the instructions, how many operands are allowed in the instructions? And how do the instruction need to be formatted into bits? So what's the way? What's the standard procedure it follows in this particular architecture? What is defined to be followed? And how many registers are there? How big is the memory? And how is the memory address? All of these are specified in the instruction set architecture of that particular machine. Okay. So instruction set architecture, we can think something like this. So you can see instruction set lies in between hardware and software. So it's something like a layer in between which facilitates the functioning of hardware and software. Okay. So this is also another picture. You can see hardware is on the bottom and high-level programming languages are top where most of the users of the computers are using. And machine program and operating system interfaces would help you in for the smooth functioning of the hardware with use in high-level programming languages. Okay. So before moving into a particular instruction set, for talking about instruction set architecture further, we'll have a general introduction into some of the terms. Most of the terms are familiar to you. What is a program? It's a sequence of stored instructions. Okay. So instruction set architecture, I think to understand that it's quite easy if you think about a microcontroller. I think most of you follows physics subjects. So in physics, microcontroller programming, it's another area which we use these instruction set architectures. So for each and each microcontroller, there's a fact sheet coming, isn't it? In this fact sheet, there are certain rules which we need to follow, like this command can be used to this instruction need to be used like this, likewise. So that's the instruction set, part of the instruction set architecture of a microcontroller. Similarly, for a computer also, so that's coming there already, because it's also a machine which runs with ICs. Okay. So a program is a sequence of stored instructions. So what does the CPU do? The main function of a CPU, if someone asks you, is the execute programs. Okay, the main function is the executing programs. It's the fundamental operation of a CPU. And a machine instruction, what's a machine instruction? It's an element of an executable program and a single operation of a processor. So you know machine instruction as an example, add AB, it's a machine instruction. Okay, so we can't say that it is directly machine instruction because it's again assembly language level. Machine instructions are with zeros and ones. That assembly language instruction need to be converted into zeros and ones for it to be considered as a machine instruction. Okay, machine instructions need to be understood by the computer. What does the computer understand? It understands zeros and ones. Okay, because using this electricity. So these machine instructions are named like that because it is understood by the computer, the machine itself. So it understands zeros and ones, so it should be a binary code. However, those are assembly is used to assemble the or the compile and convert the high-level language instruction in the machine-readable form. Okay. So what we understand, we can't understand zeros and ones. So when we are discussing about machine languages, what we actually discuss about is not zeros and ones, but those mid-level, which is assembly language instructions, which would be something like this. Add. Okay, we'll be discussing about this further in the coming slides. Add AB. Okay, this is a single machine instruction that the CPU can understand and execute. So when you're writing these machine instructions, there are again things you need to consider. So when you're writing machine instructions, there are rules. They need to be these actions you ask for the machine to do should be actually done in, should CPU should be able to do them. I mean, as an example, if you get asked the computer to divide some number by 0, can it do it? No. Okay. And there may be some additions which should result in an overflow. Okay. So it would not perform those kind of operations. Dividing by 0 and overflowing are some good examples for such situations. So we should avoid writing such commands or machine language instructions. So that's one rule. That's the first rule. And the second rule is it should be done by, we should ask from a single command line or a single instruction, one activity or one task that can be done by the CPU. Okay. So that's the second rule. I think you may have learned this in algorithms courses. So however, if you have done it, would be a revision. Okay. So machine instruction is an element of an executable program. So the program would consist of several machine instructions. Okay. One instruction is an element of an executable program. And it should be a single operation of a processor. Okay. One instruction should give only one operation to do by the CPU. And it would form the interface between hardware and software. Okay. So that is the machine instruction. And the instruction set is another term you need to know. It's a set of instructions, collection of different instructions that the CPU can execute. So as an example, add AB. So some other type is add A. What's the difference between this type and this type? In this type, you have only one operand, which is A. And in this type, you are allowed to use two operands, A and B. Okay. So like this, there's an instruction set that to define the instruction set architecture of the particular machine. And about the machine instruction elements. So what are the elements of machine instructions? What are the components of a machine instruction? So as an example, let's get this add AB. Okay. So add AB. So what are the elements? What do we have in this machine instruction? We first have the operation code. What's the operation code here? Add. Do this. Do the addition. Okay. Do addition. And it will specify the operation to be performed like add or input output operation maybe. And it is specified by the binary code. So there are specific binary codes for specific opcodes, operation codes. Okay. So the operation code, it is actually converted into binary form. Okay. And it's known as short term is opcode. Opcode. Okay. And that's the operation code, which is the first element normally. And the source operand reference. So what are we going to do this operation to? Okay. So those are called source operand references. To this, what are the source operand references given here? A and B are the source operand references. Add A to B and store in where? Maybe in A. Okay. So source operand references are the operation may invoke one or more source operands on which the operation is carried out. To this, the operation is carried out. Operands that are inputs for the operation are actually source operand references. So what is the meaning of reference? So are these values? No, these are addresses. Addresses or references. Another term is reference or address. Okay. Address or references. Reference means a memory address. And result of a reference is after doing the calculation, what are we going to do? Where are we going to store the result? So that is the result operand address or result operand reference. The operation may produce a result and we need to store that result. And the next instruction reference is, after we have done this instruction, where are we going to? So that's also a part of a machine instruction element. Okay, so this is a machine instruction. So you can see 3 elements here majorly. The other element it's not shown here. So the first element is opcode, and these are the source of references. And the result of a reference is also A here. Normally add AB means A is added to B and stored in A. So these machine instructions are normally represented in this way. So you can see this is the particular format we are using. So there's a opcode, and there are space for the operand references, and you can see there are 2 boxes allocated for operand references, and which consists of opcode consists of 4 bits. And operand reference, you are allocated 6 bits, and again as then 6 bits are allocated for the operand references. So this you may use to store A, you may use to store B here, okay, and you may use this section to store add, okay. So likewise. So 16 bits, this is a very simple instruction format. You can see in this instruction format, one field is used for the opcode, and there are certain other number of fields allocated for storing operand references. So in speaking about the opcodes would indicate the operation. They are now represented by abbreviations like ADD for addition, and SUB for subtraction, MPY for multiplication, DIV for division, load for loading data, and STOR for storing data. Okay. So these symbols which we use in assembly language is converted into its corresponding binary representation. And the operands are normally actually represented symbolically in assembly language level. So you can see assembly language instructions here. We are at RY, at the value contained in data location Y to the content of R, and we are actually doing this operation onto the content to the content of R and Y, because normally these R and Y are addresses. So they are addresses, okay? These are addresses. But we do the operation not on addresses, but on the content of the location, content of the value, content or the value, okay? So normally source and result operands can be either main memory locations, so CPU registers. So you know registers also can be used to store data in the CPU. There are locations for the registers, which is not very big but very fast memory to store data while they are being executed. Okay. So either these operands can be main memory addresses, main memory values from the main memory, or from the CPU register, or maybe be taken from an input-output device. Okay. So this is a corresponding assembly language instruction. So you can see the opcode and operand references. So these are normally references or addresses, not the values. So to do the operation, the CPU has to fetch the values from the main memory, or maybe our input-output device. Okay, whatever the address refers to. And there are 4 different types of instructions: data processing instruction, data storage instruction, input-output instructions, and control instructions. Data processing instructions And examples are arithmetic and logic instructions, and data storage instructions are memory instructions. It can be memory instructions where we would ask the CPU to store some result value in the memory, and they are used to move data between memory and registers normally. And input-output instructions are used to transfer program and data into memory. Okay. You can transfer data from input-output devices to the memory or the CPU registers. Again, if we need to do, after doing the operation, if you need to send the result to a particular input-output unit, you can use these input-output registers. Instructions. These input-output instructions can be used to send data and take data from input-output devices. And the control instructions are used to control process by the control unit. Either it can test and branch the instructions. In testing, what it does is actually, it will test the value of a data word or the state of the computation. It will test whether the status is correct for a particular calculation, or it will test the value of data word whether it is valid or not. So those are control instructions. And what are control test instructions? What are control branch instructions? So assume that we are doing a set of instruction in a CPU. Okay, assume that you are executing this set of machine language instructions in the CPU. Okay, and one of the machine language instruction, it says, depending on the decision, depending on the value of x, if x equals 1, branch to another program. Okay, jump into another machine language program and do that and come back. Okay, so this type of branchings are also controlled by the control instructions. So branch different set of instructions depending on the decision made. So there's a decision made because x has become equal to 1. So we jump to another set of instructions and carry out the set of instruction and come back. So those are the branch instructions. So that's actually some brief introduction into instructions and their instruction formats, simple instruction formats, and elements of a machine language instruction. Are there any questions? Did you understand everything? Okay, so if you have any problems, you can ask me. So I'll move to addressing modes, which is the major topic I plan to discuss with you today. So addressing modes, why do we need addressing modes? So that's the first subtopic we are going to find the answers to. So what are addressing modes? So you know now what a machine instruction is, isn't it? So in assembly language, we can, as in previously also, we put this as the example, add A, B. Okay, so this is a machine language instruction, which is in the assembly language level. So in this instruction, what is the operation? For the opcode, it's the add. What are the operands? A and B are the operands. Okay. So so are these values? No, normally these are preferences or addresses. So so addressing or putting the address here So A is a kind of address. Okay. So you know this, there's a limitation. So if you look at the a typical instruction format, there are certain bits, maybe 8 bits, okay, allocated to store the address of the particular operand, the address of the particular operand. Okay, sometimes these 8 bits may not be enough to put the whole address in. Okay, so that's why we have different addressing modes. Okay, this is the major reason. This is one of the major reasons why we need different addressing modes, because we have different operands stored in different places, maybe in main memory, maybe coming from input outputs, maybe from registers. So likewise, there are different length addresses of operands. Okay. So for the specific purposes, we may need different addressing types. So those are called at different addressing modes. So how is the, so there are a variety of addressing techniques, which are addressing modes. Another word for modes is techniques. Okay. There are different addressing techniques. So we are going to talk about them today. So we will be discussing about most of these, all of these addressing modes. First one is the immediate addressing. So before moving into this set of addressing modes, you need to I need to define some terms for you to understand this easily. EA is the effective address. So what is the effective address? Assume that there's a memory like this. Okay, this is the memory, the main memory, and there are fields, you know, and in these fields we store data. EA or effective address is the real address of the operand. Okay, it's the actual address of the location contained in the reference operand. It's the effective address of the operand. Okay, the actual address of the location contained in the reference operand. This is the actual address. Okay, so there are the addresses also we use. That's why we tell that this is the actual address. Okay. So these terms are also important. So EA, you know, is the actual address. A is the content of the address field of the instruction. That may not be the real address. So if this is the instruction format, so you know there's some specific bits allocated for opcode or the operation code. As an example, addition. Okay. So these bits would indicate the opcode. And there are certain other bits allocated for operands. Okay, maybe 8 bits. And again for the second operand, there are certain number of bits allocated. This is for the second operand. Okay. So we would store some value here, A, which should indicate the address of this particular value which is stored. Okay. So A is the content of an address field in instruction. In this instruction, the content of the address field is A. Okay, so that's the content of the address field. R equals the content of an address field in instruction that refers to a register. So if this refers to a register rather than the memory, so we would indicate not by A but by R. If A is, so this is the address of a main memory. Okay, if we use R instead of A, what would that say? R indicate the register in the CPU. In the CPU, you know, there are registers. In the registers, we can store values for operations. Okay, so the content of an address field in instruction that refers to a register is indicated by R. So what does this brackets mean? So don't think much about X. These brackets mean contents of location. X is the location. The brackets mean the contents of. Okay. So those are the terms I want you to learn. So now with these learn terms, which is EA is the actual address, and A is the whatever thing you write in the address field in the instruction, and R is the content of an address field in instruction that refers to a register. So you can use A or R dependently. And X is, within brackets, X is the content of the location X. And the immediate addressing, this is the simplest form of addressing. Operand is given in the instruction itself. Okay. So this is the first addressing mode we are going to discuss too. So now with these terms handy, so we are moving to the addressing modes. The first addressing mode we are talking about is the immediate addressing. Okay, which is most commonly used type. Well, not most commonly actually, easiest, most easiest one. Immediate, as the name implies, immediately you can see the value there. Okay. Without using any addresses, you write the value here. So there are no memory references. We don't need to go to memory or a CPU register to acquire the value. The value is given itself immediately. Immediately the value is given. Okay. So the operand equals to A. In other words, in the address field of the instructions, the value is given. Number 5 is there. So do the addition for number 5. You don't need to go to the memory and fetch the value. Okay. So we are not given the address, but we are given the value. So what does it mean by this instruction? Add 5 to the content of accumulator. Okay, 5 is the operand. So this can be used to define and use constants or set of initial values of variables. So this can be used for constants or maybe a set of initial values. So we do not need any memory reference to fetch data, and there's a very limited operand magnitude there. So that's about the immediate addressing. So what's the advantage of using immediate addressing? It's very fast. Okay, because no memory reference is required. What's the disadvantage of using this immediate addressing? There's a very limited operand magnitude. Why? So you know in the instruction itself we are writing the number, and the address field has limited number of bits to represent this number. Okay, with reasoning, the main reason why we can't store some value in the address, any value is, it's limited. It has a limited capacity. Okay, the address field of an instruction is limited. Most of the time 8 bits or 16 bits, 32 bits, depends. So you can represent each and every value you need in that given space now. So that's the disadvantage. And secondly, direct addressing. Okay. So previous one is immediate. We don't need to worry any about any memory fetching. because the value is given itself. And direct addressing, it's not like that. So you can see instruction normally has opcode and these are the operands. So you have as operand A. So the address field would contain the effective address of the operand. Okay. The address field would contain effective address. The address is given itself. Okay, what you have to do is you have to go to the memory and find the operand from the corresponding address. Okay. So you go here. A is the address itself. So to the particular address, there should be a value stored here. A is the address here, it's marked here. So you get the address from the corresponding location and then do the operation with the opcode. Okay. So the address is itself given in the address field in direct addressing mode. Add A means add the content of cell A to the accumulator. Okay. The content of cell A means the cell with the address of A. Okay. So cell with the address of A contains this value and we take that value and perform the operation. So single memory reference to access data, it's simple and there are no additional calculation to work out effective address. And that's a very limited address space. So we have to go to the memory once, okay? Because it directly gives the address of the memory. So there's a single memory reference. This is the single memory reference. It's simple. Okay, the address is given. You have to go to the address and fetch the data and come back. We do not need any calculation. And you will understand this when we are going to other addressing modes. Because some addressing modes we need to do some calculations as well. And again, limited address space. Why? Because it is limited by the given allowed number of bits. If we are asked to limit it with 8 bits, so the address should be less than or equal to 8 bits. Okay, this length, if we are asked to do it with the instruction with the 8 bits, it means you have to do that with that number of bits. So it means we can't store the address using this addressing mode if the number of bits in the address is higher than 8. Okay. So although this is direct, the main disadvantage is the limited address space because of the number of bits allowed or allocated. Okay. That's direct addressing mode. And the indirect addressing mode, so there are different addressing techniques. So the first type we discussed was immediate. The value was given itself in the instruction. We don't need to worry about going and accessing memory. And the second type was what? Second type was direct. And the address is given itself in the instruction. EA, real address equals to A. A is the content of the address field of the instruction. Okay. EA is equals to A. And now we are going to discuss about indirect addressing. Address field of the instruction gives the address where the effective address is stored in memory. So you can see EA equals A. So EA equals, what is the within brackets means? Content of A. EA equals the content of A, not A. Okay. Address does not equal directly to A. It equals the content of A. Okay. It's something like this. Okay. Assume that I want to go to Is this Channa Vidhanagamachi? Yes, I want to go to Channa Vidhanagamachi's home. Okay, assume that I want to go to his home. Okay, someone gives me instruction with the address itself. Okay, go to this. Okay, maybe he lives in 7A Nupe Matara. So if this is the address, I am given instruction, go to 7A Nupe Matara. Okay. So that is called which addressing? Direct addressing. The address is given directly. Okay. So to understand indirect addressing, let's think it like this way. So I want to go to Dushini's house. Okay. Dushini's house, and I am given instructions of Channa Vidhanagamachi's house, because the person who give me instructions knows that Channa knows Dushini very well. So Channa knows Dushini's address. Okay. So I have given with Channa's address to go there and find Dushini's address. Okay. So I'm not directly given Dushini's address. I'm given the Channa's address. So I have to go to Channa's address and find Dushini's address from Channa. Something like that. Okay. So what I am asked here is, go to some other place and find the real address of the corresponding operand. Okay. So the address is not given directly in the address field. So I have to go to Channa's address here and find the address of Dushini, which is the operand, here, from here. Okay. So I am not given the direct address EA, actual address directly, but I am given only, I am given the address of some field where I have to go there and find the address. Okay. The address is stored in that particular position. Real address or EA is stored in that position. So EA is not equal to A, but it is equal to content of A. So that's why I told you this bracket is really important. It is referred to content of. Okay. EA equals content of A. Okay. Look in A, find address A, and look therefore operand. Okay. You have to first find A and go there and look the content. So that is the next address you want to go to, and there you can find the operand value. Okay. Address is given indirectly, not directly. So indirect address is given directly in the address field, isn't it? However, here address is given indirectly. We have to go to some place, and then using that address, you have to go to that particular address and find the operand. Okay, indirect. Add content of add A means add the content of the cell pointed by content of A to the accumulator. So to check whether you have understood these three different types, I have a small exercise to do. You can read this. I'll give you a few minutes and try to absorb this information given. Normally, when we are talking about memory fields, you can draw a small diagram like this, and you can put the address values here and the content values in the boxes. Okay, now I will give you a few seconds so that you can draw the particular memory structure given, and then we'll try to answer the questions. Not here, maybe I'll give you another question, which is something, yeah, this one. You can ask the first two sub questions now. So what are the typical elements of a machine instruction? It's straightforward, so don't, we have discussed that in earlier slide, which is a theory content. So go for the second one and try to draw the memory structure. And then let's discuss about how we are going to do the direct addressing and indirect addressing modes, find the values. So you can ask if there are any questions, okay? So without taking much time, we'll discuss this. So techniques of specifying the address of data are known as addressing modes. A two-word instruction is stored in memory at address 200, 201. So let me draw this for you. So this is my memory structure. This is the place 200, and so let me use this whiteboard so that So can one of you read me the text, or I'll try? Okay, let me move the whiteboard. Okay, what does it say? It says, two-word instruction is stored in memory at address 200, 201. The first word of instruction specifies the operation code and more. So I will draw that. So this is my memory. Okay. Memory. Okay, so there's a two-word instruction stored at addresses 200 and 201. This is 200, this is 201. Okay. The first word specified the first word of the instruction specifies the operation code and mode. Okay, so this specifies of code and mode. Okay. And the second word specifies the address part. The second word specifies the address. Address is given. Okay. Code, mode, and address of the operand. Okay. So those are the information given. And the address field has the value 500. What does the address field have? It has the value 500. Address field has the value 500. The content of the memory address 500 is 800. The content of the memory address 500 is 800. The memory address 500, 800 is stored. The content of the memory address 500, 800. The program counter has the value of 200 for fetching this instruction. So I will draw the program counter here. Right. Okay, PC has 200 for fetching this instruction. Okay. The content of the processor register R is 400. Content of the processor register R. What's the value? I can't remember. Okay, we have 400. So I think the information up to now is enough for answering the first two parts. So what does it ask? Evaluate the effective address for each of the following addressing modes: direct and indirect. So in direct addressing mode, the equation is equal to E equals to A. EA is the actual address. Actual address equals to content of the address field of the instruction. Okay. So now EA equals A. So what is A? Content of the address field of the instruction here. Okay. Here. Content of the address field of the instruction. What do we have? 500. 500 is the actual address in the direct addressing mode. If you use direct addressing mode, the actual address is, if you use a direct addressing mode, the actual address is 5. Okay? The second one is indirect. EA equals content of A. Okay? EA equals content of A. What does that mean? Effective address equals the content of A. What is the content of A? What is A now? 500. Content of 500. So what's the content of 500? What's the content of 500? 800. 800 is the content of 500. So the answer will be 8. Okay, is that clear? Okay. So I think now you have some idea about direct and indirect. You can do this also. Okay, later. And in indirect addressing, you can access very large address space. Why? Because the address is not directly written here. You are referred to another place where the access address is written. Okay, you can go to a very large memory field where you can store your address. Okay, so there's a very large address space. Instruction address field refer to the address of a word in memory. So it contains a full length address of the operand. Okay, so you can suppose the length of the address field is k. So number of different effective addresses you can have is 2 to the power k. So for a word length of n, address space of 2 to n is available. So length of the address field is when it's less than word length, you can have a very large address space. Okay. And instruction execution reads 2 memory references. So that's one of the disadvantages. So in direct addressing, we can directly go to the memory address and take the operand. However, in indirect addressing, you have to go to one place and get the address, and you have to go to that address secondly. So there are 2 memory references. Okay, that's the disadvantage. So there's this indirection can be cascaded. There can be multi-level indirect addressing, something like this. So assume that I want to go to Channa's house, and I am directed to go to who is that? I can't remember. She is not there now. I want to go to Channa's house. I am given Ubudi's house address, and I go there, and she also does not have the address, and she directs me to another person who is Sandareka. Okay, so I go there, and I find the address of chunk. So like that, we can actually cascade this addressing. So here we have only one single cascading. So in here, you can say there are two, we have to go to two places to find the corresponding address. That is called multi-level indirect addressing. Okay. So that is about indirect addressing. And then about register addressing. So here access, this is not filed, okay? This is a field. FIELD, this need to be interchanged. We go here. Address field refers to register. So now you can see instead of A, we have R. Okay. Instead of memory, we have registers. So the address field has some address value which refers to a register in the CPU. Okay, this is in the CPU. Okay. Address field would refer to a register in the CPU. And the content of the register is an operand. Now, normally the content of the register is the operand. This is a very fast way of addressing. Why? If I say like that, and the effective address equation is EA equals R. It's very fast instruction fetch, mainly because these registers are in the CPU. Okay. So when the instruction is executed and when these operands are acquired, it's very fast access you can give from the registers because they are in the CPU and the size of registers are very small and they are very fast. Okay. And there's no memory access is required because registers are inside the CPU. Okay. So address field refers to a register and you have to go to the particular register, address of the register and get the operand. Okay, directly. So the EA equals R. Real address equals to R. The value is stored in the address field. So register indirect is similarly as indirect, but here we have registers instead of memory. Sorry. So content of register R would point to operand in memory cell. Okay. Since this is a large address, we can, from using this method, we can access a very large memory space. So when you compare this register indirect addressing with memory indirect addressing, so in memory indirect addressing, what we did was we went to a particular memory location and then we got the memory address stored there, and then we found that memory address and go to that particular address and took the operand from there. Here, instead of the first memory location, we have a register. Okay. So we have the pointer to the operand stored here, or the address of the operand stored here in a register, not like in register indirect addressing. In register indirect addressing, we stored the address in the memory, always in memory. However, here the first we have to go to a register and find the address of the memory location and then move to the memory and find the find the operand from there. Okay. So EA equals content of R. That's correct now. The content of R, what is stored in R is the real address. Okay, from this we can access a very large address space because you are using register to store the memory address. And fewer memory accesses than indirect addressing. So in indirect addressing, we have to go access memory 2 times. Now we have to access the register once and then memory once. Okay, so it's one fewer memory access than indirect addressing and extra memory reference than register addressing. And there's extra memory reference than register addressing. Okay. And the displacement addressing. This is a very powerful addressing mode, and that would combine the capabilities of direct addressing and register indirect addressing. So you can see the equation is EA equals A plus content of R. Okay, so in this displacement addressing, we are trying to give a displacement. Okay, in other words, so we have the instruction here, and we use two on this fields for store operand fields. So in the first field we store a address of a register, and in the second field we store a address of a memory location. Okay, so we go to the address of the register and get the value stored, and we add that to content in the address field, which is A. So A is added to content of R. A is not added directly to R. A is added to the content of R. A is now added to the content of R, whatever is stored here. A is not added to directly R. You can see that it's added to the whatever the thing is stored in R. And then EA becomes A plus content of R. So we know now the EA value, which is the actual value, actual memory address of the memory location. Okay. So in displacement addressing, we have two address fields. A, the address field value, and secondly, the register that hold the displacement. So this register would hold a displacement to address A. So that's why this is a very powerful addressing mode, which we can use to expand the addressing space. And this CPU, this displacement address can come in different forms. So we will be discussing about two different forms, relative addressing and index addressing. So this relativity comes from this R register which we are using. Depending on the specific register which we are using, this displacement addressing have different types. So the first one is relative addressing. So for the register, we use program counter here. Okay. Now we have program counter as the register in this type of displacement addressing. So relative addressing is a type of displacement addressing. Okay. So we give the displacement by PC here, program counter here. Okay. Implicit reference register is program counter here. So what does the PC hold? So in the what is PC actually? In the processor, there are registers, you know. Okay. There are specific registers for specific functions. Okay. So one of that register is PC, which is program counter. Okay. What does that store? It stores the next instruction address. What is next instruction? So what's the function of CPU? The function of CPU is to execute instructions, one after the other. Okay. Once you finish executing the first instruction, you go to the next instruction. Likewise, the main function of PC, personal, CPU is executing instructions. So after the CPU execute the first instruction, where does he go? So it's given by the next instruction address. Okay. So it is stored in PC. The next instruction address is stored in this this register, which is called the PC. Okay. So when we give the displacement by this PC, value in the PC, it is called relative addressing. And in indexed addressing, that value is taken by another register, which is called the index register. Okay. So the base address is added to the index. So the base address is A. A is added to the content of index register. Okay. Or the index. So in other terms, this is A. E added to the content of the index register. Okay. All right. So now we have talked about relative addressing, index addressing, and which are the two types of displacement addressing. And the stack addressing is related with stacks. So you know stacks which can pop and pop items and push items into data structure. I think you have learned that in data structures and algorithms. So it's a second year course, isn't it? So stack pointer is maintained in a register. So EA is equal to top of the stack in stack addressing mode. Okay. So this does not include memory references. It's very fast and however limited applicability. Why? We need stacks to function with stacks to use this stacking addressing mode. Okay. When the specific time, if we use this stack addressing, we need to have a stack. Use the stack there. Okay, so in this exercise, let's do the rest and stop. Okay. So as we discussed so far, we know the direct address in the effective address or the real address of the direct addressing mode, and we know the effective address of indirect addressing mode. Now register indirect addressing mode. So in register indirect addressing mode, what's the equation? EA equals content of R. Okay. So if I draw this again, so I'm not drawing the whole thing. So this is 200. Okay, it's quite difficult to draw it. I'll use the board. Okay, so we have two address instructions. So we have two. Okay. So the first one specifies the code and the mode. And this one has the address field. Okay. is 500 as I remember. In 500 we have stored 800, isn't it? So what does it say? The program counter has the value 200 fetched in this instruction. The program counter PC has 200 for fetching this instruction. Okay. So the program counter normally stores values for fetching next instruction. Okay. So to fetch in this instruction it has 200. So to fetch the next instruction, what does it have? 202. Because it's a two-word instruction, so you know. So when it loads the first instruction, it should load 200, 201, 4. Okay. So the next instruction address is stored, should be stored in 200. Okay. The content of process register R is 400. Processor register R has the value 400. And the content of the index register XR is 100. In XR, we have 100 stored there. Okay. Evaluate the effective address for each of the following addressing modes. We have done the first two. Okay. We are going to third one. Register indirect, relative, and index. Register indirect, relative. Register indirect, third one. What's the equation? EA equals content of R. So what is in R now? 400. 400 is the answer. What's the second one? Relative addressing mode. In relative addressing mode, what is EA? A plus content of PC. What is A? 500 plus content of PC. 202 equals to 702. The fifth one. This was fifth one. Indexed addressing. In index addressing, EA equals A plus index or content of index register XR. A is 500 plus XR is 100. It should be 600. Okay. Okay, so you can read this. So those are the content I to talk there today. So if you have any problems, you can ask me.